Hey guys, okay, welcome to today's video. Before we even get started to talk about what we have today, I just want to know how you guys are doing. How are you doing health-wise? Hope you're fine. And how's your programming journey going? I hope it's going smoothly. All right. So, in a bid to keep, seeing what we can do to help you guys make progress in this journey. That is why I'm doing this video, and it is on bit manipulation. So that is what we are going to look at today, the concept of bit manipulation. I hope you are ready. Before we even dive right into the project, we are going to look at the concept. What does it entail? Bit manipulation. So when we talk about bit manipulation, we are talking about, especially in C programming, we are talking about how to access and manipulate individual bits of data. Okay, what does that really entail? What does that really mean? It's involved using specific functions, or you want to use specific functions. You want to read, you want to write to, you want to modify, you know, individual bits in a data. And what do I mean by bit? I keep mentioning bit. A bit is simply the smallest unit, you know, the smallest unit of data that can be stored in a computer memory. That's basically what bit is. And you should know that you have another called byte, B-Y-T-E. And what is that? A byte basically is unit of measurement of storage of memory storage, and 1 byte equals 8 bits. So bit is the smallest unit, then followed by bytes you have kilobytes, megabytes, and the rest of them. So 1 byte equals 8 bits. So what are the applications of bit manipulation? Where do you, because all of these concepts you are learning, they have applications. So we are going to look at a few of them before we get started really into the project. So one of them we have there, it's what you are looking at, what you are staring at on the screen right now, which is what? Error detection. So how does it do that? You can use bit manipulation to detect and correct errors in your data, right? In algorithms, you use bitwise operations to calculate and checksums and verify the integrity of data, so that you don't want to you don't want to put out an error laden or error feed data out there. So the second one quickly is you can use that in cryptography. You've heard of cryptocurrency. You use that to encrypt data as well as decrypt data. All right, you've heard of cryptocurrency, the node encryption, how that works. So you can use bit manipulation in that aspect. So the third one we quickly look at is data compression. So that's what, how does that work, you may want to ask. How can you use um bits bit the concept of bit manipulation in data compression? Take for instance, you can have a chunk of memory, and that memory, you have redundant data in that memory. You have what you want to store is not up to this space, but it's just taking up a larger space than necessary. So you can use it to reduce the size of data files, or for transmitting data over a network. So you can use it to compress such data. So the next one, you can use it in memory management. How do you do that? You can use it to manage how much storage you allocate, how much memory you allocate to a data, and as well as deallocation. So all of these are done using malloc function of allocation and the allocation of memory. Then you can use that for, which is the most commonest, bitwise operations that allow you perform logical operation on individual data. You have the or operator, you have the AND operator, you have the XOR operator, and so on. So these are basically the major applications. There are others, but the major applications of this concept of bit manipulation. I believe that's clear. At least you have grabbed a little understand what the bit manipulation concept does in C programming, as well as how you can apply that. So having said that, we close that up and we dive right into this to start working on this. I'll have a little video to talk about the quiz section. You can access that in the channel. So first things first, like we go ahead and do we create a readme file, readme.md. So this is it. You can put a chunk of information here to explain what it does, but for the sake of this video, I'll just make it straightforward and simple, straight to the point. Just it's a readme, right? And just basically introduce what that project is all about. So I'll have this as my readme. Once you are done, you can escape column WQ, you save and quit. So the next immediate file we are creating is the main.h file. So vi main.h, what does that do? Like already, the main.h file is going to house all of our prototype that we have here. That's the first one. So this is the second prototype. This is the third one. This prototype are to guide you. All right. So you're going to pick all of this prototype. Pick all of them. Yeah, all of them. And the rest of them that are done. And you're going to include them in the main.h file. So you see, these are what you have here. These are the prototype that are being included in the main.h. So once you are done, you can do your escape column WQ, you save and quit. So before we now start looking at each individual task and how they work. So the first one we have there, guys, is this 0 binary to uint.c. So what are we doing there? We want to write a function that converts a binary number to an unsigned integer. So we're giving a prototype here. B is pointing to a string of 0 and 1 character, and we are returning a converted number, or we return 0 if there is one or more cars in the string B that's not 0 or 1, or B is null. So go ahead and do vi, then the file name 0 binary. All right, 0 binary underscore to underscore uint.c. Okay, so just go ahead and hit enter. So this is the content of that file, guys. First, we are including the main.h file. Why are we doing that? The main.h file have our main.h file houses our prototype, so we have to include that in order to reference the files, the prototype we put in the middle. Then we have the comment section, which is this, that is Betty compliant. I follow the Betty documentation style. Okay, so after that, we go ahead to the main function, and I'm going to tell you what is happening. Just a second, let me. Okay, I want to put that on visual block mode so that I'll be able to highlight this that we talk about it. So this line is the start of the function, and the function is named binary to uint. So what does this? It takes a single argument. It takes a single argument, which is a pointer to a character string, and that is B. So it takes a single argument, and that single argument is a pointer. That's this asterisk symbol that shows a pointer to a character string, and the function is expected to convert a binary number represented as a string into an unsigned integer. So we want to convert a binary number, and that binary number is represented as C, which is the asterisk B to an integer number, and return it. Okay, so that's what we are trying to do. So after that, we declared some variables. I believe you can see that the first one is int a, the next one is unsigned int num. So these are the variables. So we then go ahead to initialize the value of num to 0, then after that we have this if statement. In this line we have if statement. Okay, it checks, that line checks if the input b, which is the binary string that we are talking about, b, is not a valid pointer. That is, if it is not null. Okay, then if it is null, it means that there is no input, so the function will return 0, indicating an error. So that is if it is null. So after that we have a for loop. So the loop goes through each character, of a, is going through each character in the binary string, each of them one after the other, until it reaches the null terminator, which is 0. So it goes through them one after the other after initializing the value of a to 0, and we are looking at the b at index of a. So it goes through all of them until it reaches this null terminator, and at the end of the day, it's going to increment the value of that 1 to it at every point it goes through that loop. So then we have the if statement here. We have this if statement. So what is happening there? Within this loop, it checks if the current character in the string is not 0. If the current character that you are accessing, if it is not 0, and if it is not 1, which means that it's not a valid binary digit, and that if that's the case, the function return what is going to return 0 in this line. It's going to return 0 in this line. Then we have a second for loop. So this second for loop, this second one that we are now, what that does is that is what does the actual conversion, right, that we want to do. It convert the binary string to an unsigned integer. That's what this for loop does. So after then we have this num. This is a bitwise operation, and we are shifting the bit of the num variable one position to the left. So this, we are shifting the bit of the num variable one position to the left. This two less than sign. So then we multiply that, which multiplies num by 2. Okay, then the if statement here, we check if the correct character in the binary string is 1. This if statement. So this b index a, if the correct character is exactly 1. If it is, then we add 1. This num plus equals 1. Then if it is exactly 1, we add 1 to the num variable. So after we do that, then we return the value of num. So we return the value stored in the num variable. So at the end of the day, we have successfully done that, which is printing converting a binary number to an unsigned integer. So once you are done with that, you can do your escape column wq. That is supposed to be lowercase, guys. wq. So you save and quit, you exit. So having done that, you can move to the next one, which is this. Write a function that prints the binary representation of a number. So this is it, and I'm going to pick that name, print underscore binary dot c. So yes, this is it, guys. It's going to show this. In this case, we have two functions, unlike the first one that we had one function. Here we have two functions. So what this code is doing, it defines two functions. The first one is this. The first one is called, the one I'm pointing at now, underscore POW. Then the second function is this, where this void, this print underscore binary. So in the first function, we have, okay, these are comment section, which is Betty compliant. So the first function, which is underscore POW, it takes two arguments, right? And both of them are of the unsigned integer data type. The argument and base are power. So then after them, we declared our variables, and the first one we have there is the num variable, which will return an unsigned long integer. Okay, I was forgetting something. The function, the return type is unsigned long integer. Then back to the variable, the second variable is a, which will return unsigned integer. So then we go ahead and initialize the value of num to 1. That's what this line, num equals 1. We initialize basically the value of num. We are going to set it to 1. That's what the first line is, that line num equals 1 is going to do. So we go ahead and do this. We use a for loop, and for a equals 1, value of a we set to 1, and as long as a is less or equal to power, then we add 1 to that a plus plus. We are adding 1 to it. So then we come down here, num asterisk sign base is that it multiplies the num by base. So num, this num asterisk equals to base is going to multiply num by base. That's num times base. So that's what that is going. What that does is it raises the base to the power of power, right? We declared power as an, in the function argument. So at the end of that, we are going to return num. We are going to return the value stored in the variable num. So back to, we are going to move down to the second function, which is print underscore binary. And this function have one argument, which is an unsigned long integer n. And this function, the return type is void. That means it's not returning anything. So we have integers, two unsigned long integers, divisor and check declared, and we have a character variable, which is flag, which are declared. So what you want to do now is that we initialize the value of flag to be 0, like you are seeing here. So the value of flag is initialized to, yes, the value of flag is initialized to 0. So then we have this line divisor equals underscore power, two sides of. So what we are looking at here is that we are going to, get the value of the unsigned long integer. So if we get that, then we are going to multiply that by 8 and subtract 1, and all of that we are going to store in this variable divisor. Okay, we are going to store all of that in the variable divisor. So we use a while loop, and while divisor is not 0, we check and this line. This is a bitwise operation anyway. Lighting can be okay. Let me use the visual mode to alight so that you can see that. Okay, so I'm here now talking about this check and divisor. So what does this do? The line checks if the current divisor bit is set in n, if it's set in n. So it's going to perform a bitwise AND operation. So this is this AND. this upper sound that you are seeing, that is a AND operator, bitwise AND operator. So if the result is equal to divisor, it means that a bit has been set. So if the result is equal to divisor, so if check, which is the result, is equal to, that means we have successfully set a bit. So we set flag to 1 and underscore pucha to 1. So we print 1 using underscore pucha. So after that, we are going to use the s. After if that is not the case, then we use s. And what we are doing here in this line is that if flag is exactly 1 or divisor is exactly 1, then we are going to put print 0. Okay, we're going to print 0 using pucha. So then this line divisor, this again a bitwise operator, divisor, what this does, this does look like a greater than sign, which is not. It shift the divisor right by 1 bit. Okay, it's going to shift the divisor right by 1 bit, which moves to the next lower bit position in the binary representation. So it's going to shift that to the right by 1 bit. So yes, after doing that, that will mark the end of the program. So that is it. The code defines two functions that effectively helps to print the binary representation of a number. So once you are done with that, you can do your escape, shift column WQ is supposed to be a lowercase. So you save and quit and you exit. So that will be the second one. So we quickly move to this next. And what we are doing here, we are writing a function that returns the value of a bit at a given index with that prototype. So what I'm doing now, guys, I'll get the name of the file to get underscore bit dot c. So here we are including main.h, like I said earlier, that has the prototype that you are using. So these are the comment section, which are Betty compliant and follow Betty documentation style. So the name of the function, guys, the name of the function is get bit, like you have here. So this is it, get bit, and that function, it has two arguments, and the first one is an unsigned long integer n, the second one is an unsigned integer index. So then we declared two variables. The first one is, both of them are unsigned long integer variable, divisor and check. These are the variable we declared. So we go ahead to use an if statement. What this is doing is that if the index provided is greater than the maximum index allowed, okay, if the index, this if index size of if the index provided is greater than the maximum index allowed for an unsigned integer, okay, then that's what the size of an unsigned is going to check. So to ascertain if the index provided is greater than the index of the unsigned long integer, it calculates the maximum index by multiplying the number of bits in the unsigned integer by 8. Okay, then it's going to subtract 1 from that value. So after doing that, if that is not the case, then it's going to return error. It's going to print -1, which shows that an error has occurred. So then we go ahead to do one. This a left shift bitwise operator. Okay, here the variable name divisor is calculated. It's by setting the divisor variable to be 2 raised to the power of the index. So we are doing this using the bitwise bitwise left shift. This is it. Let me show you that. Let me put that in visual mode. So you see this is the bitwise left shift. So what we are doing here, we are calculating the value of divisor. So by setting the divisor variable to be 2 raised to the power of index. All right, so that is what that we do. And the next line, which is check equals n ampersand, that is a bitwise AND operator again. And what that does is that it's going to check if the bits are the index. I mean this AND operator is going to check if the bits are the index power in n is set to 1 or not. If it is set to 1, it's 1. If it's not, that means it's 0. So it does that by using a bitwise AND operation between the divisor and n. Okay, so then we are going to use the if statement to check if the check variable is exactly equal to divisor. So if they are equal, it means that the bit at the specific index is 1. So it means that the operation was successful, and we are going to return 0 at the end of the day. So we're going to return 0 at the day. So what does this mean is that we are defining a function that get bit that check if the specific bit in a given number is 1 or not, and will return the result. So we're going to return the result. So that's what is happening here. I believe that you at least have an idea of what is going on. So save and quit, column W, and we move to the next one immediately. The next one, we are writing a function that set the value of a bit to 1 at a given index. So going to pick the file name set underscore bit.c. Okay, so yes, so this is it, guys. Okay, so we are including main.h into this file, and again we have the code documentation, which is better compliant. So we come down to talk about the function, and if you look closely, the function name is set underscore bit, and what we have, this function, it has 2 arguments. Okay, it has 2 arguments, and the first argument is a pointer to an unsigned long integer. This n is a pointer to an unsigned long integer. Then we have the second argument is a pointer because it has this asterisk sign. You can see it. The second argument is index, which which is an unsigned integer. Then we came here to define a variable, which is set bit, and that will be an unsigned long integer variable. So these are the that is the variable we declared, and we go ahead to use the if statement. And here, if index is greater than size of long int multiply times 8 minus 1. What are we doing here? What is the meaning of that? So what that line does is going to check whether the index is greater than the max index allowed in an unsigned long integer. I believe you understand what we are talking about there. Okay, let me go into the visual mode so that I've highlighted this issue I'm talking about. It's going to check whether the index is greater than the maximum index allowed in an unsigned integer. That's what the size of, it's going to check the size of an integer. Is going to ascertain if index is greater than the maximum index allowed for an assigned long integer, to ensure that you are not trying to set an invalid index. So if it is not, then no, if that is greater than that, then it's going to return -1, which shows that an error has occurred. Okay, going to return -1. So after that, then you go ahead to set bit equals 1 minus 1. This is a bitwise operator, this two less than sign. So what that line does is that it calculates a bitmax, that set bits, which is the bitmax we are talking about, by left shifting the binary digit 1 by index position. So that's a left shift bit operation. So it's set a single bit at the specified index to 1 and all other bits to 0. So it's going to set the binary digit 1 by index position. Is set a single bit at the specific index to 1, and every other bit is going to be set to 0. Okay, then we have this line, this asterisk n equals asterisk n, or you have an OR bitwise operator, which is this vertical line is an OR bitwise operator. So the line perform a bitwise OR operation between the original value pointed to by n and the set bit. So it's going to set the bits at the specified index to 1 while leaving all other bits unchanged. So that sets the value of the bit to 1 at the given index. So if the operation was successful, we return 1 at the end of the day. So that is it, guys. Look through again. Like I said, the link to the description, the link to the source code will be in the description. You can access it. So watch the video to the end. I'll always leave important information at every point in the video that will guide you. So the link will be in the description. Please, the source code are there, so that I'm trying to see how you can understand, have a basic understanding, not just have access to the link or all of that. So I will exit column WQ, save and quit. So we're going to move to the next one, which is this for clear bit. Sorry, vi for clear underscore bits dot c. Okay, I think my clear is not well spent. CL, not CK. Okay, clear bit underscore c or bit dot c. All right, so this is it. This is the file. So what are we looking at? We're including main.h, and okay, I believe that std live, that might be just to be on the safer side. So we have the code documentation, which is better compliant. Then we have the function, and the function name is clearbit. So in the function, as you can see, we have two integer. We have two arguments in the function. So the first one is a pointer to an unsigned long integer n, and the next one is an unsigned integer called index. So we go ahead to use the if statement. As you can see here, if index is greater than size of n multiplied by 8. So what we are trying to do there is that we are we are trying to check if the value of index is greater than the number of bits in the assigned long integer, which is represented as n. So we are checking if the number of bits in the assigned long, the number of bits in value of index is greater than the number of bits in the assigned long integer pointed by n. So it does this by calculating the number of bits using the size of n times 8. So if that is the case, if index is greater than that, it's going to return a -1, which will stop the program. But if not, we continue and we go to this asterisk n, this ampersand, which is and in and operator in bitwise operation. So that line is perform the actual operation, this line. And what is the actual operation we are talking about? To clear the bit at the specific what? Index. That is what we are trying to do in this particular function. We want to clear the bit at a specific index. So this is the line that actually does that. So then the one this one that looks like 2 less than sign, not really less than, what we are trying to shift the bit position to the left. Okay, we are shifting the binary number 1 to the left by the index position. So then what that we try to achieve is to create a number with only the bits at index set to 1. So at the end of the day, after that, we're going to return 1, which shows that the program was successful. We have successfully set the value of the bit to 0 at the given index. So that's what this program does. And look through it, and at the end we are going to exit column WQ, we save and quit, and we look at the next one, which is flip_bit.c. So I'm going to do vi flip_bit.c. Oh, sorry. I think I didn't display that rightly. vi 5 flip underscore bit dot c. Okay, so what we are trying to do, we want to write a function that returns the number of bits you would need to flip to get from one number to another, the number of bits you will need to flip to get from one number to another. So this is it. Please watch to the end to get the explanation one step at a time. Watch the video to the end that you will get the explanation that we are trying to give. So here what we have, we are including the main.h. This is the comment section we have explained earlier. Then we have the function here, which is flip_bit, and it has two parameters, which are both unsigned log integers. Both of them are unsigned log integer. Then we go ahead to declare the variables. The first one, we have an integer variable which we called a, and the next one is a count bit variable which is initialized to be 0. Then we have another variable called current, which is an unsigned long integer. Then we have exclusive. That exclusive is n, which more like raised to power m. What that does is that it calculates the bitwise operation talking about this. Okay, it calculates the bitwise the bitwise exclusive or of the two input numbers n and m. So we talked about or operator, and operator, and x or operator. So we are trying to do the bitwise or operator of the two numbers n and m and store the result in the variable named exclusive. So whatever we get from that, we are going to store in the variable exclusive. So we used a for loop, and what we are trying to do there is that we initialize the loop counter to what? 63. Okay, the initial value will be 63, and we keep looping as long as a is greater than or equal to 0. We keep looping. So then we decrement a minus minus, we decrement the value of that by minus. So the loop is used to examine each bit of the exclusive variable, and from the most significant, which is 63, the first one here, 63 is the most significant, to the least significant, which is 0. So that is going to loop through that. Then after that, we have this line current equals exclusive, this this one that's look like double greater than sign, which is not, is a right shift bit operation. And what we are trying to do here is, in each of the iteration of the loop, the code right shift the exclusive variable by the value of a. So it right shift the exclusive variable by the value a, and we are going to store whatever we get there. We're going to store it in this current variable. And if current, we use this and bit operator, which is this ampersand sound, checks if the least significant bit of the current variable, which is, what is the least? Like we said, the least significant is what? Is 0, while the most significant is what? 63. So check if the least significant bit of the current variable, which is this line, is set to 1, meaning that the bit is different from the bit different between n and m. So at the end of the day, we are going to do count bit plus plus. So if the condition in the if statement is true, then it means that a bit need to be flipped, right? So the count bit variable is incremented by 1. At the end of the day, we are going to return the value stored in count bit. We are going to return the value stored in the count bit. So basically, the code calculates the number of bits that need to be flipped. That's the bit that need to be changed in order to convert one number into another. So that is it, guys. You can research more on the code. That's the explanation. Believe that you can grab something from there. So I'll save column WQ. But is it, like I said, the link to the source file will be in the description. So we move to the next one, which is, okay, I think time is fast spent, so just have to do this quickly. Write a function that checks the endianness. So first we have to look at what are we talking about. What do we even mean by endianness in the first place? I believe that that name is not endianness is not really something you've come across or you've seen in recent. So we are going to explain that in simple terms. So what is endianness is refers to the order in which bytes are stored in memory. Talking about endianness, refers to the order in which bytes are stored in memory. So there are two main endianness schemes. We have the big endian and the little endian. So you can, research more about that, but just know that it's the order in which bytes are stored in a computer memory. So there are two the big endian and the little endian. One of them store the most significant byte is stored in the lower memory, while the least significant is stored in the highest memory, while the other, the least significant is stored in the lower memory, while the most significant is stored in the highest memory address. So I just explained that. That's the little difference between the big endian and this little endian. You can research more about that so that you understand how that works. So just going to show you the code before I talk about something else. I won't waste much further time. vi 100 get underscore endianness dot c. Oh, sorry. Oh, okay, I'll just click on continue. WQ. Sorry, I'll remove this just a little right there. Okay, just let me remove all of this. ls minus a. I want to, there are some swap files I'm having already, so let me just remove them. Okay. I'm not getting to see all of that, so let me clear. So vi 100 get underscore endianness dot c. Okay, so like we said, we have explained that endianness refers to the order in which bytes are stored in memory. So this we are trying to check the endianness. We are checking for the endianness in this program, in the function, and we are not having any parameter. So at the end of the day, we return an integer, value at the end. So we have two variables. The first one is an integer variable named a, and the second one is a pointer to a character variable named b. So we initialize the value of a to 1, and value of b is we have a character pointer, and we use the and bitwise operator. A, then we turn the pointer to the value of b. Okay, so that's the explanation I can give. You can research more on that. All right, basically we are trying to check the endianness. So do column wq, save that and quit. So we are done with. So for the crack me, to solve the crack me, you see that is correctly done. I will leave. I have a separate video where I talk about how to resolve this crack me theory question. I'll leave the video, I'll link it in the description of this video. So look at the description carefully. You will see the link to this crack me file to solve that. So thank you so much. Okay, before I go, you can, after you do that, you can do git add dot, you add all your files. I'm not adding, and I've done that already. So you do git commit minus m, then and put in your commit message. Let's say update or whatever commit message you want to use. Just do update. Then you hit enter. Then after that, you do your git push, which is going to push your code to the remote. Okay, so once you have done that, you're going to check, and they'll be rightly checked, and You can join us to learn. I'll leave the link to that Telegram group in the description. So again, the source code will be there too. So I believe that this explanation we show you, we enlighten you on how this bit works. So thank you so much for watching. I'll see you in the next video.